Hello, everyone. I'll be talking to you about network layer and the routing consideration. This is a pretty fundamental a lecture about the routing. What I'm talking to you about the routing that already existing, but I'll be talking to you in more detail. How does the routings perform more of a conceptual level? Okay. So let's get started. There are different types of routings. There are static routing, source routing, flood routing, and within those routings, especially in the source routing, there are different algorithms to find the path from the source to the destination. One of the approach is the Dijkstra algorithm. Another approach is the Bellman-Ford algorithm. I'll be going over those two algorithms in more detail. And those two are readily available. And each been around for a long time, and those routing algorithm has been around. I don't know, for a pretty long time. Okay. So all this routing can be, are done on the layer three, and I'll be talking to you about it. And especially, let's go about static routings. Routes are computed only once, and basically it's a static, it does not change. Basically, program into a switch routing table, it just sit there unless someone changes the routing. It just sit there, whether is the traffic is increasing, decreasing, or there's a congestion or not, it does not change. Okay, and it's a suitable if network topology traffic pattern do not change much. So it's pretty stable. There is no traffic's going up and down. There is no really congestion. So static routing, it tends to be um, pretty good at that because it doesn't have to exchange routing information. It doesn't have to exchange status information. So it's pretty simple. When you set and the routing will be done, you will take the same routes. Okay. And the source routing, this is very readily available. Source routing is that any of the node can make a routing decisions. So any of the nodes can be a sender. This typically happens and layer three routing. That's why you need a routing protocol to exchange routing information between all the nodes. And any of those nodes can be a sender. So routing information is exchanged using different routing protocol like uh, there are a lot of different, one of the, outdated routing is a RIP, RIP routing was, it's been used for a long period of time. It became obsolete. So there are different routing protocol that is used to exchange the routing information. So each node would have a same topology information. Okay. So route is specified within packet header, and switches read the packet header and forwards the packet according to the route. So before it sends packet, the routing needs to be determined and using different algorithm. It could be a Dijkstra algorithm or Bellman-Ford algorithm. It has to be determined previously before you actually send out the route. So this is very popular, suitable when sender wants to send certain route, for testing or avoid all the routes. You can, source routing can, avoid, route, avoid congestion if needed. And to do that, there has to be some additional constraints built into it. A lot of cases, quality of service routes has a number of constraints, which has a delay requirements. It doesn't, it can have a certain congestion. It can have a certain packet loss. So to do that, you need to have, routing protocol avoids all of those routes, okay? So a cost is an extra field and packet header. Processing is burden because sender has to, discover the route. In this case, I'll be talking to you more about it. And two, flooding is basically what it says is flood. If you just once you have the packet, just send it to everyone. It's like a local area network. I mean, it grabs the packets, it gets the build the packet, it send it to everywhere. And basically, the pack, you don't know where the packet is going. You send it to everywhere. You hope that one of those packets arrives at the destination. It's very simple. No need to have a network information, not like a source routing. You just send it, and robust failure because these packets is sent to every node. So if one of the nodes not able to deliver to the next node, that's fine. There's maybe a neighbor node send it to the neighbor properly. A shortest path is always found doing this way, but it's very costly too, because source node broadcast the package to all the neighbor, and and all the neighbors broadcast the package to all of his neighbor. So there that means packet go around in the network for a long period of time. So you wanted to prevent the infinite number of the packet going around, for example, going around a circle, right? So it cannot get out. Okay, so you can do that is make sure the browse packet it does not come back to the incoming link. It cannot go back, it only can go forward. Okay. And also packet has a unique ID and source number and the sequence number. You can use that to make sure that a packet does not go backwards. Okay. Another thing is a packet keeps counts. And if it keep counting, if you're doing certain number of a hop in the network, it just after the certain number, after the 10th node, the node destroys the packet after it reads that there's a number 10 in the packet. This is a 10th hop. Okay, so another way is make sure that the broadcast along the spanning tree. I don't know you learned about the spanning tree. Spanning tree is a subset of a connective graph that connects all the node with a node cycle. It doesn't have any loop. You just go to the node only at one time. Okay. A spanning tree is must be maintained, update, make sure that it doesn't it doesn't create a problem or leave out any of the node. Okay. So flooding as this is one of the example. For example, in the flooding, A send it on one first packet to this node sends this is more of a sequence number, send the package to all those neighbor, but it doesn't send it back, right? He send it to the forwarding. In this case, it send it to the forwarding as well. Once you receive, you send it. So you see a lot of a same package being received, right? All of those links. So they will create a lot of congestion, and they're very inefficient as well. So if you have a spanning tree, something like this, so A sends the packet, it reaches this node, send it to second time, so it reaches this node. So A send it to this node send it to all other nodes. So the packet receives at every node only at one time. It doesn't receive multiple times. So this is a spanning tree. This is a tree-like structure. It doesn't create any loops, right? So it reaches only at one time. Okay. So there's also the random routing. Outgoing link for the package, chose randomly. Let's say it has a node and it has three different links attached to it. It just sends it randomly. You don't think about it. One time, send it to the link on the left. Maybe next packet send the link on the first in the middle and send the link on the right or something like that. So outgoing link is chosen randomly. Obviously, this is not the smart way to send the packets. So probability based on link rate or the fixed link information, it distributed uniformly, and hope that the packet arrives at the destination during any time. So it's unpredictable when the packet will be arriving at the destination in this case, right? So one good thing is it's pretty simple and it does not require any network information because it sends out randomly, and it's very suboptimal. It's not optimal, and also the loop is a big problem, just like the flooding. But you gotta make sure that there is no loop is happening. Okay. So this is random routing. Another is deflection routing, hot potato routing. How hot potato. Once you hold a hot potato or hot goguma, it's very hot, right? You just want to give it to someone. It's the same, same analogy is that objective is to get rid of the packet quickly as possible once it arrives. So try to minimize the delay, and that doesn't mean that it's very optimal getting to the destination, right? Also, another thing is minimizing the chance of buffer overflow, and but in a packet, since it doesn't really think about where it's sending to, it's just sending anywhere, anywhere. So, and it may not get to the destination. It can combine with static routing, and each packet has a assigned link. Is more than one packet that contain the same link, the 160 is others are deflected. So if there's a causing congestion, so other packet is going to the different direction. Okay. So another thing is shortest path routing. This is the most popular for the source routing. Is you got to assume the knowledge of the entire network. What I mean is that each node has a knowledge of an entire network. Okay. So whichever node sends the information, since it has a topology, entire information, an entire network, it can make its own independent decisions, right? That because of the routing protocol, it distributes all the matrix to all the nodes, so every nodes know which nodes are existing in this network. Okay. So network is represented by a graph of nodes and links. Each link is assigned to link the more general cost. Objective find the route between source and destination with the smallest total link, also least cost. Least cost does not mean that it's a distance. It can be more of not the distance. It could be a delay, which is the quickest. It's not just the distance. So cost could mean anything, and I, it could, you know, it could determine, it depends on the, designer of the network, how they want to determine the cost. Something could be a combination of delay, packet loss, and distance, and all of those. And the two widely used algorithms today, we're going to talk about the Dijkstra algorithm and Bellman-Ford. These are the pretty well known. You should know the Dijkstra algorithm at least, right? So let's look at the least cost routing. Is, as you can see, these are the network topology, right? These are the different link costs in there. Cost could be the a delay, or like I said, right? Delay, the distance, or whatever. Here's the spanning tree with the different costs. It chooses only once. Okay, let's look at the Dijkstra algorithm. So each node, you need to kind of pay attention on this part, is that each node has a label X and Y, where X is previous nodes, is previous node means a neighbor node, which is a previously, and Y is a distance from the source node along the best known path up to the time. What is the distance between the source, right, or the cost from the source node? So label is a tentative or permanent. Is permanent when we represent if it thinks it's a shortest path part of the shortest path, you will include that in the list, right? Algorithm proceed to find the shortest from the source node to all other node, increasing order, taking one at a time. So what happened is it goes through a number of stages. You could call it case stage. So we have found at the case stage, you have found the case shortest path from the source node. These nodes are included in set M. M is a more of a collection of nodes. It could be, you could think of it as a database or, in a bracket with the collection and make sure you want to keep that. So at the next stage, shortest path is found in a node, but it's not in the M. Then what you need to do is you need to include it in the M, okay? And so at the end, what happened is M includes all the nodes, and that becomes the shortest path fit spanning tree. Okay, let's go in more detail. How is it done? Okay, so in Dijkstra algorithm, let's say a source node is one. There is and when you talk about the link, you just think about the C and IJ. So IJ is, I'm sorry, this is the cost. Cost is between IJ means a node I and J. It's between that, this is the cost. Instead of permanent nodes found so far, this M is a group, no label. This is a previous node, X, and Y is a distance from the source node to this node, okay? So basically, when you look at the flowchart, you look like this. Initialize all the node with the minus and the infinity. I'm sorry, yeah, minus infinity, and add node 1 to the M because that's the starting point, right? From the last node, add to end, update the label at the neighboring node, right? Neighboring, not all the node, neighboring node, right? Shorter distance can be found. Change node label to the shortest path. What is the shortest route? Okay, you need to determine that. After that, among the nodes not currently in the M, if it's not in the M, choose the node with the smallest distance in the label. What is the smallest distance? Make this node permanent add to M. I know it's kind of confusing, but this is my way of explaining it in, verbally. But let's look at it, more in picture, okay? So, Dijkstra algorithm, this is the example graph, and the, 1, 2, 3, 4, 5, those are the node number. 5, 2, 3, 2, 3, those are the, what do you call it, the cost, okay? So what happened is in initialization node, you basically add 1 equal to M is group on node for the shortest path. You add that. So what happening is you figure out the cost, and one hop is what are the one hop from 1. So look at it. So 1 is from the 2, 1 is a previous node, right? 1 is a previous node from 3 because it's taking this. 5 is the cost. 2 is the cost. So 1 dash 2. Over here is it's a neighboring node is 4. 4 here. The cost is 1 from the source, right? Cost is 1, previous node is 1. Cost is 1 here too. So I'm talking about just one hop. So as you can, this is a 1 in 1 hop, okay? So choose basically which one has the lowest from out of this. Which one is the lowest cost here? Is a 2, 5, 1. I guess this is the lowest cost. So happens to be node 4. You add a node 4 as a permanent. Okay. Okay. So let's go on. You update from the last node update right here, right? 4 is the last. From over here, you update one hop. Okay, one hop. So one hop from the why does it keep doing that? So one hop is that from one hop over here is 4 4 because previous node is 4, cost is 4 because 3 plus 1 is 4 4. But over here, this is one hop. Previous node is 4, cost is 2 because here's the 1, here's the 1. When you add up, becomes a 2. So over here is the previous node is 1, least cost is 2. So it's not going to update to 4 and 3 because the 2 is lower than 3, right? 1 here, 2. it could become 3, but the 2, which is from 1, is the lowest cost. It's not going to change. Okay. So, out of this, this is already 4 is already in there, right? 4 is which one is the lowest cost from 1 is this node, right? Oh, this is the lowest cost, but it's uh you can add to this from the source. This is the lowest cost, right? So it's a 2. So you add a 2 becomes a permanent, right? 2 becomes permanent. So from 2, update the neighbor from 2 here. You update it here. You update it. You update it here. This does not change because when it comes from 2, it's 5, which is higher than 4. So what's going to do, it's going to keep the lowest one, right? If it's over here is previous node is 2, but the cost is 2 plus 2 is 4, but 1 is the lowest cost, so it's not going to make any change. So it advertised the neighbor and basically it stays the same. So now it's thinking about which one has the lowest cost. This one's included, this one included. From this, which one is the low cost? It's this one, right? So it connects there. So it adds 5 as a permanent. Okay. So from the 5, it advertised to the neighbor. Okay. If it advertises the neighbor, what happened is from A5 advertises neighbor, it used to be 4, 4, but it becomes 5, 3 because 1, 2, 3, which is a cost is less than 4. So it changed to 5, 3. For over here is 1, 2, 3, 4. If previous node is 5, least cost is 4. So this is changed, right? Okay. So which one has the lowest cost? Because we included this one, we include this one, we include this one. So 3 or 6 has which one has a low cost? So it's a 3, right? So we add a 3 in there. So you update the 6. I mean, there's nowhere to go. So this one has the lowest cost because it's 2, not 5, right? So you make it 6 permanent. So what happened is look at all the bullet. The tree structure looks like this, right? So if you want to get to 1 to 2, it goes there. If you go from 1 to 3, it means it needs to go to 1, 4, 5, 3. That's the least cost. If you want to go to 6, it becomes 1, 4, 5, 6. That's the lowest cost. So this is a spanning tree of least cost routes. So, in a Dijkstra algorithm, it's going to look like this from node 2, node 3, node 4. It tells you where it needs to go, okay, which is in table form. So let's take a look at the Bellman-Ford algorithm. This is different than Dijkstra algorithm because this is more of a distance vector algorithm. In a Bellman for optimal principle, path is optimal in any segment. Along with this path must be optimal between 2 nodes. Algorithm perceive to find the shortest path from source node to all the nodes in increasing order of number of hops. You probably don't know what I'm saying, right? So I mean, just try to, keep up with me and we'll have some easier way to understanding is you can go back on the video, kind of like read it again after I go over it visually, right? So find the shortest path of 1 hop, which is max, then shortest path of 2 hop, which is max. So you increase by 1 hop, 2 hop, 3 hop, you will find the shortest path. It will stop when the next iteration does not change anything. Okay, it does not change anything. So that's what happened. So let's take a look at it. You need to proceed with the iteration. Each iteration is you reach out to one hop, you reach out to two hops, reach out to the three hop. There's the number of iteration, okay? So each hop, each node is responsible for updating its own label at each iteration. When you do one hop, each node needs to update it, okay? A node looks at the route through all its neighbors. I mean, also, what's my one hop neighbor? And you'll choose the neighbor with the shortest route. At end, it doesn't change, okay? The result of the shorter path training tree root at the source node. Okay, what's gonna happen is, initialize all node at the, hyphen and infinity, except the source node is, hyphen and zero, because it's zero hop, right? That each node calculates a route through all neighbors. Choose the shortest path, update the neighbor if necessary. And you do this until there's no more change, okay? Let's take it visually. That might be the easiest, is that, for example, once you initialize, there is a minus infinity on all of those, but it's a minus zero on over here, right? So what happened is that this initialize is I'm sorry, it's first iteration is one hop from node one. This is one hop. This is one hop. This is one hop, right? Each node calculate route through all neighbors, chooses the shortest route, update neighbor if necessary. Okay, so one hop here and one hop here and the one hop here. So what happened is those are the shortest path, right? Shortest path to the origin, or to the source. It doesn't change. So let's take a look at when I push the second iteration, which means is it going from second. This is first, right? It goes up a second, second, second. This one goes to all of this, okay? The second iteration, oh my God, things change. What happened? From this one, this one, this one, this one. Second iteration is going to two hop. In this case, this was first aggregate. This is a two hop, 1, 2 here, right? Here's one here. This is second iteration. This is second iteration. This is second iteration, right? From here is this is second iteration, second iteration, second iteration. Okay, so it used to be 1, 5, but it became 4, 4 here. The issue is that, as you can see, the 5 and 4, the cost is lower. So out of all of those, it found that the previous node 4, coming 1, 4, which has a lower cost, so it override 1, 5 and put 4, 4. Okay. So for this one is over here, one hop from here is this one, but this one could be one hop, but this is too expensive. 5 here, it could be 6. It's too expensive. For best bet is excuse me, is 4, 2. Previous hop is 4, its cost is 1, 2, becomes 2 here. Okay, so this is the lowest cost. This is the lowest cost. So he looks at it, all of it, every time he does iteration. And this one becomes a 310 because before that it was nothing. But over here was next top, right? This is the next top of the number 3, right? So it becomes 10, right? Becomes a 10. But this one has not reached here because it was coming from 4, only a 1 hop from there. Okay. So it becomes a 310. It has not count. So when you go to third iteration, okay. When you go to third iteration, it further changes. It changes this one and changes this one. Let's take a look at what happened. Okay. On third iteration means it's a number 5, and the third hop is this 1, 2 equals iteration third hop. But rest of them no, because this is only a second. This is third here. The second. So there will be a third iteration. It's the third one. It does advertising, 1 hop. Okay, because 1, 1, 1, which is it's 3, which is lower than 4. So it becomes 5, 3 because the previous node is 5. The cost is 4, 3. So what under this one is that it used to be 310, but if it's coming from here, is a 1, 2, 3, 4, 4, which is a lot lower than 310. So it becomes 4, 4. I mean, I'm sorry, 5, 4, because 5 is the previous node, 4 is the cost, right? So after the additional iteration is all in, there's no 4 hops, right? For another, no iteration. So what happened is they're going to draw the, bold line. As you can see, is 1 is a previous, 1 is previous, 4 is a previous here. 5 is a previous, so it becomes, at this spanning tree, just like a Dijkstra algorithm, okay? So Dijkstra and Ford, Bell and Ford, it comes out with the same answer here. It just use a different approach, and the table form it looks different too for the Bellman Ford as well. Okay, so today I went over the different routing algorithm and how routing types are existing, like a random routing, flood routing, static routing, and there's a source routing. And when you study the networking, there has to be a routing protocol and the routing involved. This is just the fundamental part, and you just need to build on top of Dijkstra and Bellman Ford. Nowadays, there are tons of different routing protocols out there. Depends on different NIM, is a different QoS. So, this is just the beginning. Okay. Well, thanks for listening. Okay, let me test all the slides. Let me see. Uh, Stop sharing. Okay, thanks for listening. Have a great day.